So we've seen that we can differentiate a function of several variables in many different ways, one derivative per input variable. But what about second derivatives? Right? I mean, in the single variable context, a second derivative can tell you a lot of things about what the graph is doing. So we should think about what second derivatives, how to compute second derivatives, and what they mean in the multivariable context. So let's just do this with an example. So here's a function, f of xy is x squared times sine of y. To get at a second derivative, well, we're just going to have to calculate a derivative twice. So let's start out by calculating the derivative with respect to x. So notice that I'm using this system, or this symbol partial x is how this is pronounced, partial x. This is like a verb or a command. It says we are taking a derivative with respect to x, and the thing we are taking the derivative of is this function f. So what we're about to write down is partial f partial x. So we took one derivative with respect to x, and so take a derivative treating y like a constant, so that's going to be 2x times sine y. Okay? Well, now that we've taken a derivative, we could take a second derivative. So partial x again. This is partial x of partial f partial x. So I guess we would write this partial x of partial f partial x is how we would write this. And this is, well, we just take the derivative of the first derivative with respect to x. So that's going to kill off this x, so we get 2 sine y. All right. A little notation, though. It's kind of clumsy to write out all of these partials like this. So the usual thing to do is, since these look like fractions, so they are not fractions, but since these look like fractions with two of these partial symbols, the traditional way to condense this notation is to write partial squared f, and then in the denominator it looks like we have partial x times partial x, even though that is not what this means. But it looks like it's partial x, and so we write partial x squared. So this notation means the derivative with respect to x twice. Another way to write this, if you like that subscript notation that we talked about before, you could write this f sub xx. And that would be the name for this partial derivative. All right, so what about in the y direction? So what if we took this and did a partial derivative in the y direction? So partial y, that would tell us partial f partial y. And we would just take the derivative of this, this expression, but treating y like the variable and x like a constant. And so that's going to give us x squared times cosine y. And then if we wanted a second derivative, well, we just hit it with partial y again. That would give us partial squared f partial y squared. So just take another derivative, treating y like the variable and x like the constant. So that would give us, let's see, the x squared part slides outside the derivative because it's behaving like a constant, and the derivative of cosine y is minus sine y. Okay, so there's our second derivative with respect to y. But this isn't the whole story. The thing is, at each stage of a derivative, we could differentiate by either variable. So that means there are two more second derivatives. We've calculated 2 second derivatives, but there are actually 2 more second derivatives. So if we calculated the first derivative with respect to x, we could calculate the second derivative with respect to y. So that would be partial y. So the notation for this would be, let's see, partial the derivative with respect to y of the derivative of f with respect to x. So we would take our expression for partial f partial x and take its derivative with respect to y. So that's going to give us 2x times cosine y. Okay, so another way, so the sort of more abbreviated notation for this would be, so 2 more abbreviated notations for this would be, we could condense our partials and write this as partial squared f partial y partial x. Or the other way to write this would be partial yx notice I'm putting these in the order that matches the partial notation. Okay, so the final second derivative that we could take here, this final second order derivative, is to do our first derivative with respect to y, but then do our second derivative with respect to x. So partial x here. So what we would get here is partial squared f partial x partial y, like this. So we'd take our derivative with respect to y, so x squared cosine y, and take its derivative with respect to x. Actually, let me move this down here. So that's going to be 2x times cosine y. Okay. Well, notice that it actually, for this example, it turned out that if we do the x derivative first and then the y, we get the same thing as if we do the y derivative first and then the x, right? These two partials come out the same. These two partials, these are called the mixed second order partials. So mixed second order partials. And for this example anyway, those mixed second order partials are actually equal to each other. Now it is a fact that I won't prove, but it is a fact that in most situations those mixed partials are always equal to each other. So that's not actually a coincidence. This is called Clairaut's theorem. If you have a function that has all partial second order derivatives and all those derivatives are continuous near some point, this is supposed to say AB. So if you have all second order partial derivatives and they're all continuous near your point AB, then your mixed partials are equal to each other at that point. And this is usually always the case for us, right? It is possible to come up with examples where a function has partial derivatives but has second partials that aren't equal, mixed second partials that aren't equal. But you have to work really hard to come up with such examples. I mean, if you look at the assumption of Clairaut's theorem here that all second partial order derivatives exist and are continuous, I mean, most times when we write down formulas for functions, they are continuous everywhere they're defined, right? So this is almost always the case, and certainly in all practical situations coming from, say, physical examples or even most mathematical examples, Clairaut's theorem will apply, and so these mixed partials will be equal to each other. So if we actually back up for a second and look at the notation that I used for subscripts, some people put these subscripts in the other order, but because of Clairaut's theorem, it actually doesn't matter which order you put them in. So because of Clairaut's theorem, if we need a mixed partial, we don't have to worry about which order the mixed partial is in. I won't prove Clairaut's theorem. There's a proof in the book. I think it is worth reading through if you're curious about it.